simple simulation with the default settings, but how can we go from there to a custom configuration that will fit your research interest or your class? You want to see something specific. So as Dave mentioned, the OpenPiton is a quite scalable and configurable infrastructure. You can see here the different configuration settings that you can have. Up, you can see that you can configure the OpenPiton chip system to have up to 65,000 cores per chip, and that can scale if you go to multiple chips to up to 500 million. Of course, going for that is going to be hard to simulate. And then based on the, Dave also mentioned we have multiple cores that you can check. Here you can see the OpenSpark T1 and Ariane 64-bit core, and these also have configuration that you can change. You can change if they have a floating point unit or if they don't have. If how big is going to be the bit width of the floating point unit, how many TLB entries, what is the size of the cache, what is the set associativity of it. Furthermore, you can configure the intra-chip and inter-chip topologies. You can have a 2D mesh or a crossbar to communicate across your cores. So let's see now how configuration works in OpenPiton. Everything happens through the Sims tool. So basically, you will have a command line configuration that will say how big is going to be the cache if you want to go away from the default configuration, how many TLB entries, if you want an FPU, if you don't want an FPU, which core you're going to be using. The default settings are set in the Manycore config that you have seen being used in the previous examples. And if you want to change it, it's at python/tools/source-sims Manycore. Examples of configuration you can see down here. So it's dustconfig_L15_size will change the cache to what the L15 cache size to what you want compared to the default one. So configuration in OpenPiton happens in two ways. One is that the Sims tool takes the command line input and exports it as environment variables, and that is when caches are involved. Otherwise, if you import a new design, your design in OpenPiton, and maybe you have Verilog defines that enable different things, you can do that by passing the Verilog defines with a specific configuration. You can do dustconfig RTL and put your own Verilog defined to configure your component or other components that already exist in OpenPiton. Now, PyHP is the infrastructure we use. It's a Python preprocessor to generate more complex RTL. If we are creating multiple tiles, we are replicating code, right? So that's a tool that we can use to provide this, to enable this in an easy way. And you can say, well, the Verilog generate kind of does the same. The difference between PyHP and generate is that we see the output. The generated output by the process code can be seen at the end, and that helps with debugging. So PyHP, what it does, it embeds Python segments. It allows to embed Python segments inside Verilog code. So you'll have your segment wrapped around the less than % and closed by the % greater than symbol, and you have your Python code that generates on the standard output Verilog code that will be changed on that section and combined with wrapped around Verilog code. So let's go deeper and under the hood on PyHP. So PyHP reads the environment variables and creates global Python variables that you can use. So you see here, first line, just read from the environment, create a config_L15 size global Python variable. And then when you go to your combined Verilog and Python code that we have been using the .pyv suffix to designate these files, you can write Python that immediately uses these variables, process them, and you can do immediately a print statement to create a new Verilog define. And you can also use for loops to generate more complex code for that. So you can write your template of Verilog, have designated points that you're going to be replacing, and then have a for loop. You can see down here that takes the template, makes modifications, and prints it out. So that creates a very flexible environment for you to write Verilog code. And let's dive immediately to some examples of how do you do configuration. And by default, a lot of the configuration is very easy to do. You want to go we've seen right now the default example is a single core, a tile with a single core. What if you want to go to a multi-core, many-core system? So what you only need to do is like define what is the x and y dimensions that you want to expand to. So you do a sims, that's sys many-core, that's to use the default variables we have been using, and then you say 16 by 16 just by the does x underscore tiles and does y underscore tiles to go to a 16 by 16 tile. The does Ariane configuration will choose the Ariane core over the OpenSpark T1 that comes by default, and then you'll be using the does VLT build to use the verilator to build your simulation. Another example is going to be, okay, I have a many-core, or I know how to do a many-core. How do I change the topology of the interconnect? You can do that using the DAS network underscore config flag. And by default, the 2D mesh is used. And you can see here that we changed to a crossbar configuration. So all of the variables, the cast configuration, the TLB, what interconnect to use, how many cores to be put in the tile, everything can be done through the command line. So it's very easy to play around, like get started with the system and see how things change. So another example, the default cast configuration, you can see it here, the L1I, L1D, L1.5, and L2. And let's say we want to decrease the L2 size because we want to run an application, see, okay, if I change the L2 cast size, what happens in my application? We just go with the same way, does sims many-core, does VLT build to use verilator, and then does config underscore L2 underscore size. And you see we changed from the 64 kilobyte to a 16 kilobyte cast. Just by that, we can get going with a smaller size. So it's very easy to configure the basic things of a system. And finally, we can run now an example, a smaller example that you can use in your laptops. And if you do on your build folder, sys does sys many-core, does VLT build, does x underscore tiles 2 equals 2, does y underscore tiles equals 2, does Ariane, you will create a 2x2 configuration that we can run then the hello world many-core this time. That is a variation of the original hello world that you've run. So if you go ahead and run that, it should take some time. And when it finishes and you see the configuration, that you passed the test, you can do a cat, the fake UART, and see the output